All right, so today is Monday the 27th, and when is the test? Tomorrow. Okay, and so it's going to cover everything we've done since I took over class on November. So I'm going to run through turbine engine inspection and exhaust system inspection, and then I'm going to have to go through a review really fast to make sure that we don't go past 10 o'clock. That's a great question. No, you're not going to use a Scantron. I decided I'm not sure how I'm going to write the test. There'll be multiple choice questions, but you're just going to mark the test. So no, you don't need a Scantron. I recommend you do it in pencil so you can erase when you make a mistake. But if you do it in pen, you can just X out what you don't like and then circle the one you do like. If you've X'd everything out, then I'll just decide that you didn't like anything, and you'll get them all wrong. So yes, so that's a good point. So tomorrow, the test, it's going to be closed book. You can't have anything on your desk except pencils and erasers and ink pens. And then I'm just going to stand up here, stare at everybody, and make sure they're not looking at places. And then after you take the test, you'll give it in, and I'll grade it that night, and then we'll review the test the next day. We will not come back after you've taken the test. You're still here until the 50 minutes is up, even if you're not here. All right, so turbine engine inspection. So the disc is the part of the turbine that the blades are all connected to, and the best way, there's two good ways, according to this, to inspect a disc, and one of them is visual, which we've talked about, and you've done visual inspections, and you've also done dye penetrance. What's interesting is that this is the first time the lecture said NDT. So NDT is a three-letter abbreviation for non-destructive testing. Let's see, that's an I. Is that an I? Is that an E? Non-destructive testing. Can anybody name one other type of non-destructive in testing other than dye penetrant or magnetic particle, which we talked about last time? Eddy current and ultrasound are the two that come to my mind. Yes. Yes, tap test would be a non-destructive testing, I think, although tap test probably won't work for turbine discs. Generally speaking, for the turbine disc, cracks are not allowed. And of course, where would we go to look to see how much pitting could we fix? I know this is tough. Somebody brought it up the other day. The current manufacturer's manual. We're going to cover that again during the review. Any questions about this slide? All right, blades. You'll note that the part I like here is damage due to heat and so this would be a great test question. Turbine blades, what are the two things that make turbine blades change shape or lose their original shape? And one of them would be heat, and another one of them would be centrifugal force. Generally speaking, with metals, the harder you heat them up, what happens to how hard the metal is? It gets soft. And in fact, at some point you can get it so hot, if you're spinning it around, what will happen to the length of the turbine blade? They stretch. Yeah. So a test question about stress ruptures. And stress ruptures are found on the trailing edges and on the leading edges of turbine blades. And this is a good example of a stress rupture. And here would be, it's a crack that's on the leading edge or the trailing edge. The blade's been overstressed and it's coming apart, and that's one way for it to come apart. Does anybody have any questions about where stress rupture cracks? A rupture means it's coming apart. It's not staying in one piece. Like you rupture a water balloon, or you rupture a spleen in a football game because somebody elbowed you really bad. Have you ever played in a football game where somebody elbowed you bad enough to rupture your spleen? Yes? Okay. Was it a fatal accident for you? Now, it probably wasn't fatal if you're still here talking. Other questions on this topic? I got to keep going. I'd love to talk about football. That's not a true statement. I made that up. All right. So we already talked about stress rupture cracks, and we're not going to worry about how long cracks are. We already talked about deformation due to over temperature and centrifugal force, so we don't have to cover that one again. You can also look for waviness. Is an example of a defect on a turbine blade. And of course, this is actually out of an FAA question I saw. Watch out, blending repairs are not the same as waviness or deformation. So if you're inspecting a turbine blade, be careful that you're not looking at a blade that's been repaired and going, oh, it's wavy, when in reality there's just some metal that's been replaced. Generally speaking, you're going to look at individual blades in particular when it comes time for overhaul. You need to do your best. You need to reinstall the blades in the same spot. And therefore, you're probably going to need to number the blades before you take them apart. So I'll say that again. Generally speaking, when you take turbine blades out to inspect them, you need to put them back in the same place you got them. It's going to be a whole lot easier to balance that turbine disc if it was previously balanced. Any questions about taking blades out and putting them back in the same spot? All right, so okay. So the book talks about curling, and the lecture talks about curling, and we've also talked about stretch. But there's also this thing called creep. So we're all talking about the same thing. If this is a turbine disc, and here's a turbine blade sticking up off of that disc, and let's look at it this way. So here's a shaft. And so here's the engine, and we've got a turbine blade sticking here, and we've got turbine blades going all over the place. The airflow is going to push it, and it's going to tend, as this blade gets hot, the top of the blade is going to tend to curve. It's also going to tend to stretch. So if we look at this portion really closely, and we look at that blade, and that's not a good picture. Let's try a different picture. Let's just erase it all. So if here's the shaft of the engine, looking at it from the side, and there's turbine blades sticking up, turbine blades sticking down, here's the engine case. And we look at this section right there, and at an exploded view, here's the engine case. The blade, and I'm over-exaggerating, this is called creep. You can also call this stretch. You can also call this curling. And we're not talking about the curling that you have those big rocks that you push on ice in the Olympics. That's a different kind of curling. Has anybody ever done that kind of curling? The blade bends back, and it's doing this because it gets hot, so creep. Hot metal. We have centrifugal force, and then that third thing we have is, I'm trying to think, high velocity gases. So if this blade gets hot, that means it's going to bend easier. If we blow air across it, it's going to bend the blade in this direction, and centrifugal force is going to pull it outward. So getting hot is really what's allowing the blade to change shape. And the two forces that are acting on it, centrifugal force and high velocity gases. So I'm going to go back to this slide. That's, you know what, don't put that on there. Because the high velocity, yeah. Here, I'll tell you what. The question's going to be look like this. Can you name 3 things that tend to cause turbine blades to change shape during normal engine operation? And you're going to say the blades get hot, centrifugal force pulls them outward, and then high velocity gases tends to bend them. No, I'll have a few multiple choice, but this one will be like name 4 of the 3 different factors that turbine blades and make them change shape. And you'll only write down 3 of them, and you'll get one wrong. Any questions so far? I know I'm going fast. So one way to check for creep or to check for stretch is to see how close the blades are touching the inside of the engine case. Because it's not just the fact that the blades are going to get weaker from this occurring, but now they're going to start rubbing on the case, and if they start rubbing on the case, then that's going to be a really good place for the case to fail. If you start scratching the snot out of the inside of the case, it's probably going to break at that point. So you're going to measure clearance. Turbine blade tips to case. And you have to use white fingernail polish to do this. It's actually in Appendix X-ray of FAR Part 43. Certified aircraft mechanics under FAR Part 43 may not do turbine blade to engine case clearance tests unless they're wearing white fingernail polish on at least one digit of the hand that's actually doing the testing. So you need to just keep a bottle of white fingernail polish in your toolbox. Yay, we got through the turbine section. Now we're going to go to the exhaust section. Wow. Cracks, warping, buckling, or hot spots. So this would be a great test question. You're inspecting the exhaust section. 4 things to inspect on exhaust. We got cracks and warping and buckling and hot spots. Sorry, I'm trying to go too fast here. My handwriting is off. All right, if you see hot spots on the tail cone, and that's effectively that's the last piece of metal on the exhaust pipe, is the exhaust pipe, then there are 2 things that could be causing this. Either you have a problem with the fuel nozzle is malfunctioning, or you have some other problem in the combustion chamber, like a liner is cracked or broken and not there. And when you're looking for hot spots, it's not that you can't see them on the outside, but you're also going to look for them on the inside, and you can look here and you can look here. So if you see hot spots in the exhaust, and you look at the exhaust and the exhaust isn't cracked or anything, then the likelihood of why it's getting too hot is because, like for instance, if there's a fuel nozzle. So let's say that here is I'll draw a picture of an engine really fast. So here's a turbine engine, we got compressors, we got a combustion chamber, we got some turbines. And if we have an exhaust nozzle, a combustion, or a fuel nozzle that is, and it's not having a really nice flow pattern, instead some of these are clogged, and we have fuel that's not atomizing, and it actually comes through, and it's still liquid and burns up somewhere in here, it could be really hot right there. Because what we really want is for all of the combustion to occur before the air leaves the combustion chamber, because we want this cool air not to just burn, but we need this cool air to mix with the hot gases. So by the time the air goes through the turbine section and out the exhaust, it's still stinking hot. You know, it still might be 800 or 1,000 degrees Fahrenheit or Celsius rather, but it's hot, not so hot that the exhaust can't handle it. The other, yeah, okay. I think that's enough on that side. Any questions? Sweet, now it's a review. If we have time, we'll come back to that. Everything you always wanted to know but jet engine maintenance test questions, but we're afraid to ask. All right, so we'll see here. I know we're going to go through this fast, but I'm concerned we won't get through all 79 questions that I want to get through today. So let's see. Procedures, repairs, and reciprocating aircraft engines are similar across different engines and across different manufacturers. For reciprocating engines, how you clean spark plugs, is that usually the same? Do cylinders bolt onto the engine cases from Lycoming to Continental? Is it really similar? Do they all have cooling fins from a Lycoming to a Continental that look really similar? Do they all have overhead valves? Is the valve train and camshaft system pretty much identical? Do they all have rods? They all have aluminum pistons? You either have a wet sump oil system or a dry sump. Do you have oil pumps bolted onto the accessories into the accessory? Tell me, from manufacturer to different manufacturers of reciprocating engines, are the way you would do maintenance on these engines reasonably similar as compared? How about turbine engines? So for recip engines, it's pretty similar, but for one turbine engine to another turbine engine, if I replace those words and put in turbine engine, what would you say then? You'd say false, because one turbine engine to the next, pretty much completely different. So what must always be used by the mechanic when you're doing turbine engine maintenance? And in addition to white nail polish, oh, it didn't show up. There it is. That's what I wanted to show up. I want you to write in 3 words. Current. Can't be the one from 4 years ago, unless it's a current one. Manufacturers. And it's implied. If you wanted to write down current manufacturer's maintenance manual, you want to put the word maintenance in there or repair, I don't mind. But you got to use a manual, it's got to be from the manufacturer, and it's got to be current. How about this next question? What's in the cold section? Let's put it this way. What's the last component of a jet engine that's still in the cold section? I'll give you a hint. It comes after the compressor. But it's before the combustor, before the combustion section. It's the diffuser. So intake, compressor, diffuser. Oh, if you had a pneumatic system on this and you were pulling pneumatic power off of it, would you be pulling air power off of it after you're burning the fuel or before you're burning the fuel? Before you're burning the fuel. Let's see what I wrote. Oh, I remembered pneumatics. I'm so happy. Yay. Any questions about that? How about hot section? What's the first component in the hot section? Well, the fuel nozzles are in there, but what's the fuel nozzles installed in what section? The combustion section. You could call it the combustor. What comes after the combustion section? The turbine blades. Are there stationary blades in there too? I probably won't ask that way on this. What comes after the turbine section? the exhaust. If you had a turbojet or a turbofan and you wanted to land and slow down really fast, what extra component would you have? Sometimes it's on the exhaust, yeah. The thrust reversers. If you don't know the answer to this question, you haven't been paying a lot of attention for the last 2 weeks, but that's okay. If you don't know the answer, go ahead and raise your hand. We'll just laugh, and then I'll tell you the answer. Okay, no one, everyone's happy that they know the answer. Sweet. If you're not, go ahead, ask. I know everybody wants to know. I only want to know what the question is. We're going to say 400, 600 degrees Fahrenheit. And notice in this question, I put a big one. Because if you've only got 1 or 2 stages of compression and it's on a small engine like an APU, it's going to be a couple hundred degrees colder than this. But we don't really care about that. We want high temperature bleed air off of big jet engines. Any questions on this slide? Draw a stick diagram. I love drawing stick diagrams. Let's see, don't forget the fan. I almost forgot the fan. And we need at least one shaft in here, and we need some compressor blades, and we need some turbine blades, and we need some kind of a combustion chamber, maybe fuel nozzles. We need an exhaust duct. Let's see, in the question, I think I told you the parts I want. Oh yeah, you got to include the intake. All right, so here's the intake. And I got on a big old jet engine, you notice I put turbofan. So I'm not going to ask you to draw any other kind of an engine except a turbofan. So you're going to need, and I'm going to give you this list. I'm going to give you this list. And it'll also say you have to label it. The fan, the compressor. Fortunately, you already have this diagram in your notes. Combustor, if you write combustion, that'll be okay. And the turbines. I'm not gonna go into the fact that there could be 2 separate spools and 2 separate turbines. I'm pretty happy right now for this. Don't ask me what Mr. Aswin's going to put on his final exam. I'm sure he'll write it, so it'll be very difficult to pass. See, I'm sure we have to label the exhaust. All right, so I'm not going to ask you to put in the fuel nozzles. And draw an arrow. Ooh, they draw an arrow showing where the bleed air leaves the engine, and label it bleed air. So where's the bleed air come off of? Generally speaking, what part of the compressor section? The high pressure area, so the end of it. So I would have the bleed air like this, bleed. Now me personally, I'd probably draw a duct, but that instructions say draw an arrow. So I'm not going to ask you for anything more than just drawing an arrow. But that arrow needs to come out of the last portion, that last 10-20% of the compressor section. And it says label it bleed air. So I'm going to label it bleed air. Whoops, wrong one. Oh, draw an arrow where the EGT probe is usually placed. Sorry, is this confusing? Do I need to put this on a blank slide? Hopefully you're just referring to the existing diagram you already have. What are the EGT probes? What does EGT stand for? Exhaust gas temperature. I wonder where EGT probes get put. And the exhaust. So I'm just going to draw one like that and one like that. And somehow I'm going to write EGT. And look, it says label the arrow EGT. Don't worry, I'm not going to just unlabel it like I did in class. I'm going to give you a list of every component I want you to draw, and it's also going to say label all of these components. Draw the 2 EPR probes. Holy mackerel, I'm going to go to a different color here because it's getting crazy. So just draw what looks like, and I don't care if it looks too big, a probe in the intake, and where's the other probe go? in the exhaust. So you notice I even put engine station 2 and engine station 7. Which one of these is engine station 7? The farther from the front, the bigger the number. So this one up here, that would be engine state, you know? Yeah. And that one right there would be EPR probe. Engine station 7. See if I got one last thing on there. Nope. So there. Any questions about the one diagram you're going to have to draw on the test? You're going to have to draw and label the intake duct, the fan, the compressor, the combustor, the turbines, the exhaust, where the bleed air is coming out, where the EGT probe is, and you're going to have to draw and label the EPR probes. All right. Anybody who's not in the first, who's not in the third or fourth semester, can you answer this top one? Which 72, hut 1, hut 2. Decide what. Don't have to write what paragraph in part 43. I'd hope I had this coming in here, but slowly. So, darn, I answered it. The two biggest differences between line maintenance and shop maintenance. Line maintenance is generally you do it while the thing is still bolted onto the aircraft. So you don't have to take it off the aircraft and then work on it and then put it back on the aircraft. And then the second thing is that you can usually do line maintenance in a short period of time, as in on one shift. So that airplane's only out of service for the night shift. That way it comes in at 10 o'clock at night, the 8-hour night shift, works on it, fixes it, and it's back ready to go at 6 a.m. for the first flight. Anybody have any questions about that possible test question? And just to be really, really clear, this review, in this review, I probably won't be able to ask you every question that we've reviewed. I'm giving you as many of the possible questions that I can come up with. All right. Can anybody answer the last one here? Why is it important to keep work areas clean when you're doing maintenance on turbine engines? So nothing gets sucked into the engine, so that's the intake. How about on the rest of the aircraft? If you have a disorderly and non-clean work area, what would happen to the rest of the engine, Jocelyn? What could happen? Yes, keep going. Something can get down inside of the engine. Yeah, you have things get into the engine that aren't supposed to be there. I would probably use stuff is more than contamination. That is correct. Generally speaking, you need to clean the engine so you can see the metal parts. That is correct. So we talked about this the last day, I think, before Thanksgiving. Does anybody know that question, the answer to this question? One. You do pretty much all the time. Prevent leaving tools in engines or airframes. And then you would do what? Now, how many tools do you have at the beginning of the day? And yeah, if you want to use the word inventory or count or confirm at the end of the day that you have all your tools, I would accept any way you wanted to explain that. And what's another great way to prevent leaving tools inside of aircraft, engines, or airframes? Well, I think if you have a really organized toolbox, you can do what Wyatt suggested pretty easily. Well, you got a toolbox, they're all in one place. Don't leave the tools sitting on or in the engine or on or in the airframe. Don't set them down in the engine, on the engine, in the airframe, on the engine. If it feels like you really need to do that, you ought to get a mat, rack, or something, tool on top of that thing, so that you can see it easily and go, aha, all my tools are right here, and I didn't spread them out across the aircraft. But for test purposes, we're going to say the second thing is don't set your tools down or lay them down inside the engine or the airframe or on it. Oh, wait, there we go. So you had a turbine compressor. The engine's been in service for a long, long time. What's the number one indication? Well, how do you tell what's the indication of being efficient? Say that again? Well, or can't I just push, if it's not a FADEC, can't I just push the power lever up till I get the EV I want? Go ahead. GT for the same power setting. So in a reciprocating engine, in the little one working on in here, you go out and you fire up the engine and take off power, you just shove the throttle forward, and you go, woohoo, down the road I go. Yay. And if it gets to the correct RPM and or manifold pressure, all right. But on jet engines, you're not going to push the lever all the way. You're going to push it up until one of two things happens. Either you get the takeoff power or you hit the red line EGT. So if you're used to hitting takeoff power and EGT at 1,000 degrees Celsius, and to get takeoff power, you have to go to 1,100 EGT and then 1,200 EGT, and the red line's 1,300 EGT. Why is the engine taking 200 more degrees Celsius to get the takeoff power? One of the reasons could be there's stuff stuck to the blades. So we need to clean it. We need to do a compressor wash. So I'm going to see if I put the answer down or I'm going to say it again. Okay, so I'm going to say the answer is what's the indication? To get takeoff power, the EGT is higher than normal. Or you could say it the other way around. The EGT is higher than normal, even though you're trying to get the same amount of takeoff power. And when is the EGT going to be the highest? Is it going to be highest at idle, or at cruise power, or at takeoff power? It's going to be the highest at takeoff power, so that's where you're going to probably be looking for it more than any other moment. So we already covered the answer, one of these two answers here. What's the answer we already covered? What are the compressor has reduced efficiency? Anybody except Wyatt? It gets dirty, yeah. Things stick to it. Dirt, dust, salt crystals stick to the inside of the compressor section. So now the shape of the blades is not what the engineers designed. What's another way that the shape of the blades can get changed? Well, okay, under normal conditions, because it's been in service for a long time. You're right, if you get ice in there, but if the pilots are doing what they're supposed to, turn on the anti-ice before that. And if we're on the ground and we think it's going to ice up, we're going to run the engine or not. Damaged, foreign object damage, FOD, sucking in things that damage the blades, so there's scratches and nicks. Or what if you're an aircraft and you fly into airports that are next to beaches, and it's not the salt, but it's the sand. What's going to happen if you keep ingesting sand over thousands of hours? What's going to happen to the metal on your blades? Stationary and rotating blades, both of them, it's going to wear metal off. So now are the blades going to be the shape they were supposed to be? No. So both of these two things change the shape of the blades. One adds crap to it, and the other one takes metal away. Any questions about that? So if the engine was dirty and you did a compressor wash, in theory, change. Now, somebody else. Surely someone else in here knows the answer. That's where you raise your hand and say, I know the answer, Mr. Johnson. Y'all aren't. Doing a Three Stooges impression there? Oh, sorry. What's going to happen to the EGT if you do a compressor wash? Generally speaking, you hope that the EGT is going to, if you push the power up to the same power setting, it should drop. It should be less because now the engine's efficient again. So generally speaking, if you compressor wash for this power setting, you ought to have lower exhaust gas temperatures. Why is the answer no? So that would be a great question. So the next question that I didn't write here, I'm going to write it in, would be why? Or why not? Nah, you're going to wash it out. You're going to if you use some soap in your wash, you're going to rinse it out. What? Somebody said the word. The D word. Damage, yeah, that's right. All that foreign object damage that scraped and scoured and wore out our metal blades, your compressor wash won't fix that. So we may do a compressor wash and it may get better than it was, but is it going to be as good as new? The engine's got 1,000 hours on it since new, 3,000 hours on it since new. No, it's not going to be as good. Erosion, yes. From dirt and particles and sand. Anything that hits the blades and scrapes a little bit of metal off of it. Yes, that's eroded. Very good. So that will reduce the efficiency. So compressor washes won't bring it back to brand new efficiency. We won't see as low an EGT as we would when the engine was new, but at least it'll be better than it was. Oh, I did have that one on there. Gosh. I'm so happy. I wrote this on Thursday. Think of those music videos. I mean, the compressor wash videos we saw on YouTube. How many of those compressor washes? I think we watched 3. We watched one on a big jet, a transport category jet, 737, a Cessna Citation business jet, and on a PT-6. On 3 engines, how many of them during the compressor wash, as in burning fuel, not spinning, but burning fuel? And how many of them? 0. So generally speaking, do you do compressor washes with the engine running? No. Of course, the water and the soap's not going to do very much good in the combustion section or in the turbine section if you've got the fuel burning. All that water is going to turn into vapor, so it's going to not do a very good job cleaning in those sections. So that's why you would not want the engine running. Pneumatic starters. What kind of power do pneumatic starters take? I know this is tough. Say it without using the word pneumatic. Yeah, what kind of air? It's going to be blank and blank and blank, generally speaking. No, not where it comes from. If you were going to describe the physical characteristics of pneumatic power, you'd say that the energy in the air can be transported based on its heat, volume, and pressure. Okay. All right, so how long can you run pneumatic starters? Yeah, there's typically 0 time. There's typically no maximum amount. If you recall those videos on the PT-6, they only ran the starter for 20 seconds, and then they let it cool down because it's an electric starter motor. And what happens to electric starter motors when you run electricity through them while you're running the starter motor? They get hot, and if you run them too hot, too long, yeah, they melt, the insulation melts, and you burn up the motor. But pneumatic starters don't have that restriction. So I think on that 737, they were running it for like 2 minutes. And I'm going to bet money, since that business jet, they only ran the starter for 20 or 30 seconds, my guess is that means those engines were small enough that they had electric starter motors. So generally speaking, this is what I would put for an answer. If I asked you, I'd say short periods of time. I'm not going to ask you any numbers on this test. Wait till we get to the next test. We're going to talk about starter duty cycles. You don't have to know what a starter duty cycle is for this test. If you'd like a number, say 20 or 30 seconds, that would be fine with me. But if you said short periods of time, I would also accept that answer. I've never seen a starter motor that was electric that you could run for more than 30 seconds at a time. That's the longest I've ever seen any electric starter motor on a jet engine ever say you could operate it. But after you did 2 30-second runs, you had to wait for 30 minutes to do it again. All right, EPR. Can you tell me what EPR stands for? If you don't know the answer, raise your hand. We'll laugh and I'll give you the answer. Go ahead. Ha ha. Engine pressure ratio. Ha 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 ha. Is that why you raised your hand? Okay. EPR, engine pressure ratio. Okay, anybody except Elizabeth and Amir answer this question, because I know they know what the right answer is. You're running the engine at cruise power setting. We'll say that's 70% of, so that's a pretty good power setting. Which EPR probe has higher pressure in it, the one in the exhaust? If you don't know, this is a good time to ask. For the okay, where that's Ashton. No, well, yes and no. Not just static pressures. I think that's the next question. If the engine is running, is it blowing air into the probe in the exhaust? Okay, so is static pressure in there and is ram pressure also in there? Okay, how about the intake? Is air getting blown past the probe in the intake? Is static pressure in that probe? If the engine wasn't running, would there be static pressure in the probe? Okay, once you start the engine up, isn't the static pressure still there? Okay, now if we pull air past the EPR probe in the intake, in addition to that static, is some air getting pushed in? Yes, so what kind of two pressures are in the intake probe as well? Ram air pressure and static air pressure. Both of these, you know that the pressure is typically called PT7, over PT2. Do you know, Ashton, what that T stands for? You know what the P stands for? P is for pressure. Yeah, that's right. How about the T? Anybody want to help out Ashton? The T is what? Total. And Ashton, what are the two pressures that make up the total pressure? I know this is tough. Right. Okay. And just for fun, anybody know what is the 2 and the 7? Yeah, engine stations. So now, to answer this question, which one of these two is in the exhaust and which one of these two is in the intake? Now, anybody except Amir and Elizabeth, they already know the answer. Why? You put your hands down. Yeah, station 7 is in the exhaust, and station 2 is in the intake. So, which one of these has a higher pressure? The total pressure in the exhaust or the total pressure in the intake? Remember, I screwed it up, right? Elizabeth and Amir corrected me, and I came into class and said I failed miserably, and I cried, and I consumed alcoholic beverages, and I cried some more, and then I came to class and confessed my sins. I don't know if it's a sin, but it's fun to say that. Which one of these pressures is higher? Ashton? Yes, you're right. And you're right. It would. Yes, you're correct. Engine pressure ratio gauges are never found on any engines other than turbojets. They don't have fans or propeller blades or turbofans. You're never going to see an EPR probe on a turboprop or a turbo shaft. So your thought process is good. So the question is, somebody's got to give me the answer. Otherwise, we're just going to dismiss class and I won't give you the next 10 questions. Which is higher pressure, in the exhaust, Ashton, or... Yeah, in the exhaust. Is higher in the exhaust. At least Amir and Ashton and Elizabeth will get that one right. Wow. Look at that. The P stands for, the T stands for, the 2 or 7 for. We already did that. And each EPR probe is measuring 2 pressures. And Ashton already told us which of these 2 pressures. The total pressure, it's made up of static plus ram in both the probe in the intake and the probe in the exhaust. But hey, this is just all a review from before, right? So, what's a typical engine EPR when the engine is at idle? Is it very much? The lowest you can get is like a 1.1, let's see. Everybody's going to want to know what the test question is. We'll just say 1.2, and we'll make it easy. 2.2 if the engine's at a high power setting. Just remember, I won't ask you this on the test, but those are very generic numbers. Every engine's going to be... I'm going to... like this. Idle, it's going to be really close to 1.0. A little higher than 1.0. That help? Not taking notes. You're just going to remember till tomorrow, okay? And then you'll forget it all. Cracks on compressor blades. Generally, how big can they be? What? What's that, Evan? 0. You can't have cracks on compressor blades. Generally speaking, which part of the compressor blades can you have more damage on it and still be repairable? The inner blade or the outer blade or near the root? Outer towards the tip, you can generally have bigger damage and still repair it and be airworthy. Inner part of the blade towards the root of the blade, towards the center of the engine, is generally less. And in fact, very near and the root of the blade, sometimes how much damage can you have there? Little or none. Little or none. Any questions there? So I think this is a little change. You can do a visual inspection. You can do a dye penetrant. Or maybe you can do a magnetic particle. Only if the engine part's made out of a ferrous metal, iron, cobalt, or nickel. And if it's stainless steel, it's probably not magnetizable enough to be able to do that. So if you write down NDT as one of these 3 answers, and then you write dye penetrant at the same time, you won't get credit for NDT. Because dye penetrant is a type of NDT. Does that make sense? Both of these 2 are types of actually, all 3 of these are NDTs, aren't they? Visually inspecting it is a non-destructive inspection. What 3 types of metal are ferrous? I just said them out loud. Anybody have any questions about that? Iron, cobalt, and nickel. And that's can be, not always can be. Generally speaking, in aircraft, stainless steel parts, even though they have mostly made of iron, generally stainless steel parts in airplanes, can you magnetize them or pick them up with magnets? Most of the time the answer is no. So could you do magnetic particle inspection on stainless steel parts? Generally in aircraft, the answer is no. Because magnetic particle inspection requires that you magnetize the part. This is going to be a tough question here. You're a power plant mechanic. You're inspecting a jet engine. There's a defect on a part. You want to know if you can repair it, where would you look? I'll give you a hint. It's a 3-word answer. Current manufacturer's manual. Did I lose anybody there? Okay, you got 6 seconds, Brian. I gotta be done by 10, man. Okay, you got a power plant rating. Chris Garcia's going to do the work. What 3 things does the mechanic have to do to make sure that it's okay for Mr. or Mrs. Garcia to help? I put Chris because that could be a male or female name, right? What are these 3 things that you have to do? No, they don't have to be a repairman. No. Any human being. It excludes animals. You have to be a human to do the work on an aircraft. The mechanic has to supervise the work, right? You got to supervise the work. Well, that's defined. That's included in supervising. Name, person, in logbook entry. I was here the day I covered it. So you have to name that person, say Chris Garcia did the work. And then, I know this one we didn't really cover. The mechanic has to sign the logbook. So who's taking responsibility for this work? Yeah, is Chris Garcia going to get named in a lawsuit? Maybe, but will the FAA come after Chris Garcia? Nope. The FAA will not come after Mr. or Ms. Garcia. He's being supervised by the person who promises they did it right. Any questions about that? Hey, there it is. You got to supervise, you got to have the name, and the mechanic has to sign the logbook. It's like I knew what the answers were. An owner-assisted annual. So this one's tricky here. Mechanic's got inspection authorization. The owner of the aircraft. We'll make an assumption the owner of the aircraft has no certificates whatsoever. And you're going to do an owner-assisted annual. So what can the owner do? Well, if the owner has no certificate whatsoever, they can do preventative maintenance, but there's an overarching term. Can they change out the wheel bearings? Yeah, they can. Can they do fabric repair? Yep. As long they can do pretty much any repair or any assemble or disassemble. Because who's going to end up signing off the work? The mechanic who's supervising the work getting done. So that's the issue. So what can an owner not do? The owner specifically cannot do what? Work and supervise. That's true. The owner can't do the inspection part. The owner can't do the inspection part. So the IA has to do all has to supervise everything, and the IA has to do all of the actual inspecting. It's okay if the owner inspects it, but does the owner inspecting it count for the annual inspection? No. Does anybody tried to make this simple? I know I told a story or two last week. Any questions about this? Hopefully I'm getting closer to the end. Do mechanics usually use power tools to do jet engine repairs? 3 typical tools. Turbine engine parts. Emery cloth, files, and India stones. That's generally the only thing you're going to use to repair the inside of turbine engine parts, where you're taking metal away. I'm not going to get into what if you welded it. Because then you start saying, well, then I'm going to use the TIG welder. No. Yeah, you're not. I won't go so far as to say that never in the history of jet engines could you weld a blade, but that's one of the least likely things you're going to be. Because now you're heat treating it when you weld it, it's going to probably not be good. So, why would you use emery cloth and not sandpaper? Which could embed other kinds of metal into the parts? The sandpaper could embed parts into metal into the engine parts. Whoops, I can't spell HSI correctly. The spell checker didn't catch it. HSI is a 3-letter abbreviation for hot section inspection. So this is a very general question. I actually use this as an example on a PT6. Your engine has an hour time between overhaul. Probably when you need to do the hot section inspection, would it go all the way to 6,000 hours? Does anybody remember the example I gave in class? PT6 is that's half exactly. So you have to do that. Is that you're going to have to do hot section inspections more often than you're going to do complete overhauls. Pardon me? The parts inside the hot section inspection need to be inspected more frequently than the parts inside of the cold section. So if you don't have to look at the cold section until it's overhaul, you're probably going to be looking at the hot section parts sooner than total overhaul. Maybe once, maybe twice, maybe 3 times. Does that answer your question? I'd say 3,000 hours, or say before 6,000. You're going to have to do it more often, Jacob. Yes. Just be clear, though, you would still be doing the hot section at overhaul as well. Question? Yeah. I just want you to understand that hot sections have to be done more often. If you just wrote hot sections for this, you wrote hot sections have to be done more often than total overhauls, that'd be awesome. Or hot sections have to be done more often than inspecting the cold section, that would be fun. Life. I wrote the answer down here. I got to go faster. I guess I didn't write it down. Service life, how long will the engine last while it's being used? So I'll probably say, without using the word service and without using the word life, can you describe service life? The definition of service life is how long can you operate the engine before it needs maintenance? Add that part? Yeah. Service life is how long you operate. Hey, we're getting close. Exterior of a combustion case. Hot spots, exhaust leaks, and distortions. I know you wrote that down about 35, 40 minutes ago. Right? Interior, there was 5 things. So the question will read, name the 6 things you would be looking for inside of a combustion section. Cracks, warping, hot spots, buckling, and object. So fortunately, you already wrote that down. Can you use any old cleaning product on jet engine parts? Okay. Where would you look up to see what kind of cleaning products you could use? Wow, it's those 3 same blanks. Current, manufacturer's manual. Generally speaking, if you're doing work on turbine engine parts and it's going to end up on a shelf for a while, you generally do that. Kind of turbine oil of some kind. Let's see. Borescope inspections. Typically have to take the engine apart to do a borescope inspection. Is that true? No, in fact, the whole point of a borescope inspection, you don't have to take the engine apart. And when do you typically do borescope inspections? It's possible, but there's a more likely reason. When you think something's wrong with the engine, and you really don't want to have to take it apart just to find out. So generally, borescopes, it's not that you can't do them then, Wyatt, but generally borescopes inspection are done when you believe something is wrong on the inside of the engine. These next two are really, really difficult questions. If you're taking engines apart or putting them back together again, do you need to not drop them? You need to support them. And when you're putting them together and taking them apart, do you need to make sure that they go in correctly and don't get jacked up? Is that a term? Is that an aviation term, jacked up? Put them in straight. And everybody knows about graphite lead pencils, right? They're terrible to mark jet engine parts. And wow, 3 blank lines. Where would a power plant mechanic look to see what marking materials can be used on a particular engine? If you don't know the answer to this question, stand up. No, I didn't say talk if you knew the answer. Which maintenance manual? Nope, you missed it starts with the letter C. What kind of maintenance manual? There they go. Don't worry, I'll just take off points. Don't worry. Why would you not use metal brushes on fuel nozzles? Scratches them up, and it tends to make the holes bigger. So what will happen to the fuel coming out of the nozzles? Will it be the correct amount? No, it's not going to be the correct amount. Generally speaking, wow, what kind of cleaning fluid? Approved, yeah, it would be approved by the maintenance manual. Okay. What's the best way? You've cleaned out your fuel nozzles. You want to make sure they work right. You pump something through them and look at the spray pattern to see if it's current. We already covered NDT today, right? Is that fast enough? Of course, you already wrote this down a couple of 3 days ago. Sure I did. We already did NDT today. Generally speaking, can you have cracks on turbine discs? No, you can't. What size cracks on turbine section blades? It's just like compressor blades. Cracks, not damage, cracks. On the other slide? Okay, all right. We'll cross that part out and write down generally no cracks, just like compressor blades. And this is now 3. Can anybody name those 3? Yeah, we got heat, centrifugal force, and high velocity gases. And blade creep. The best way to describe blade creep is that centrifugal force stretches it so it's longer, the aerodynamic force push it and back. So make the blade change shape. Without that heat, you wouldn't get creep. So are the blades going to stretch no matter what? Somehow, some way, are the blades going to stretch a little? So are you always going to be checking for clearance between the blades and the engine case? So what happens to that size of that clearance as the engine's in service? It gets less and less and less. I'll give you a hint here. The exhaust section is identical to the combustion section except for, why isn't it there? There it is. Except for FOD. You generally don't have foreign object damage in the exhaust section because it's already been stopped by the rest of the engine. Hot spots. What are the 2 things that generally cause hot spots in the exhaust section? Something's wrong with the what, or something's wrong with the fuel nozzle, or something's wrong with the combustion chamber. Hi, White. It's like I knew the answer. Pencils, pens, erasers. Pencils, pens, erasers. I'd say at least 50. So I'm going to tell my friends to start at 40 after, 40 after, 40 after, 40 after is when lab start. 75. I will take the test. I'll multiply how long I took it by 3. And if that exceeds 50 minutes, then I'll take off questions. That's why I'm going to multiply how long it takes me to do it by 3. If it takes me 15 minutes, then I think students will have 45 minutes to take it. Then I'll add a few more questions. It's probably going to be about 50, probably approximately 50 answers. Approximately.